Now we have the last talk of this session given by me. And the talk is about, my name is Kun Zhang. I'm from Carnegie Mellon University and Mohammed bin Zayed University of Artificial Intelligence in Abu Dhabi. So this talk is about causal representation learning, discovery of the hidden world. And please consider this talk as a perspective in overview talk instead of technical one. I will try to share some views and your feedback would be appreciated. So first of all, let's try to draw the analogy between what we are experiencing and the scientific revolution that happened in the 16th and 17th centuries. So right now, compared to 300 years ago, what do we have, right? So we have rich data, we have a system of probability theory and statistical inference, and we have powerful computational powers, right? So we have a lot of computational resources. And if you go back, say, even 50 years, at that time, we didn't really have very good computational resources, and we didn't have rich data. So those things are unique. And then the problem is, what do we want to learn from data? And this is the key point. Later you can see, essentially, I think this part is missing right now in order to really facilitate the next step of the revolution. And if you go back to the 16th century, at that time, you can see a lot of people discover new things, include Copernicus, Galileo Galilei, Newton, Bacon, and Harvey, right? So what did they use? Essentially, at that time, they just started collecting a lot of data by making use of instruments like telescope, right? They had some data, they had some basic understanding of probability theory, they have some very basic rules for inference, formulated by Newton in his book, Principia. And then you can see they try to have a quantitative view of nature instead of a quantitative one. And if you go to ancient Greece, you can see usually they just had qualitative view of nature. And they have some methods, right, to give very clear answers to the questions. And at the same time, the study of the paradigm was shifted from studying why to how. Basically, they try to see how everything is running this way. They try to discover laws, right? At the same time, they believe that the study of why it was too greedy, right? It's too hard because you don't really have enough information. And at the same time, you can see that book production makes it possible to communicate, right, with others, and so you can easily do information dissemination, and you can easily learn from others. And then, in this way, the research community is becoming kind of more and more prosperous. At the same time, they make use of observational data, and they can do very few experiments. As a consequence, they achieve those things. Compared to nowadays, what we have right now, you can see what's missing. Basically, we have internet, we can communicate in a very good way. We have enough data, we have computational resources, and we have problems. The issue is what we are trying to achieve from such data seems to be rather limited by what we aim to achieve. For instance, we know that at the very beginning, we care very much about why. We try to use causality as a way to understand what's going on. We try to use the causality to do extrapolation, and we try to use causality to do information fusion, right? But by putting small things together to really build a big system. Right now, in most time, with machine learning, we care more about prediction. But we know that even if you care about the prediction, as long as the system is deployed, it's called a problem because the system will have an impact on human life and human society. Essentially, we care about the why, we care about the causality. The problem is whether we can really shift the paradigm from studying how back to why. It's completely possible because as long as you can really formulate the causal principles and make the causal principles technically operational so that we can reliably discover causality in almost all situations, even if there are a lot of latent variables, right? Then basically we can achieve that goal. Now let's see whether we can really achieve something. First of all, you can see the modern research on causal discovery, just discovery of causal structure, actually was very short. In 1956, Rauschenberg published his book, and in the book, The Directing Time, he formulated the common causal principle. It's very preliminary, but at the same time, you can see, yes, you can go from statistical information to causal information. And Markov condition was formulated about kind of 40 years ago. And then in 1993, Peter spotted Clark Limmer and Richard Shines published a book, Causation, Prediction, and Search. And a lot of methods were proposed there. And you can see at that time, they could only consider very limited situations, right? And in most situations, they assume that there are no latent compounder. Or in some cases, they assume that even if there are latent compounders, I don't care about where the compounders are. Instead, I still want to see the relations among the measured variables. And very often times, you cannot really make the result very informative. Okay, and then people try to go further, made a lot of concepts very clear in his book. And later you can see other methods, including greedy search method, functional causal model-based method, and some methods that try to discover latent variables were published. Okay, this is very brief history. What does it mean? It means that actually history is very short, and there's a long way to go and lots of work to be done. Why can we discover causality from data? Basically, we have to see the footprint of causality in data and try to go back. By that, I mean, we need to establish some kind of identifiability to show that if I have enough data, then I can convert it to the truth, right? So basically, all causal discovery methods rely on some kinds of instantiations of causal modularity or exogeneity in economics, modularity in philosophy and computer science, and independent causal mechanisms formulated by Bernard and basically Tübingen group some time ago. Basically, they refer to almost the same thing. Even if the system is complex in the sense that all variables are dependent, if you have a causal way to look at the system, then you can see the systems are not relevant to each other. So each system, subsystem, generates one variable from the parents, right? Their variables can be very related in very complex ways. However, now along is the causal. You know that I can change one part without changing any other part. And if they change it together, they change independently and so on. And then as instantiations of this condition, you can easily see condition-dependent relations among the variables. You can see the independent noise condition, right, in linear non-Gaussian models. And you can also see minimal changing principle and independent changing principle if you allow distribution to change across different scenarios or in non-stationary case. Now, given that, we try to say that, yes, with those principles and information you can discover from data, you can actually recover causality from data. And in almost all those methods, not almost, yeah, all of them, essentially we have identifiability guarantees, meaning that if you have enough data and if the assumptions hold true, then definitely the answer would be right. So it will convert you to the truth. Generally speaking, we can consider either causal discovery or causal representation learning, which aim to discover high-level latent causal variables. In this way, we can just categorize them according to the three dimensions. One is what kind of data you have. Do you have ID data generated by a single distribution, or temporal data, or multi-distribution data, right? So in the latter two cases, we have non-ID case. In causal discovery, as long as you can go beyond the ID setting, the problem is simpler, right? Because causality is about changes. And the second one is whether you have parametric constraints. If you have a linearity constraint, then clearly you can benefit from it. But right now, in many cases, you may want to drop the parametric constraints. Still, you can do something. And the last one is whether allow latent compounders. So in classical causal discovery, usually you don't allow latent compounders, but now we have to do so because what we can observe is just a small part of the world, right? The interesting latent causal variables are usually hidden. And this is my view, and I think we should, maybe it's nice to go this way. The traditional use of causality is somehow circular. You believe causal relation happen to some variables. You go there, you collect data for those variables, you try to verify relations or quantitative influence, right? But in practice, especially in AI for science, what you can do is that follows. I can only collect the data, right? For those variables I can understand. And then based on such data, I just try to infer what's going on, no matter whether the variables, the true underlying meaningful variables are observed or hidden. I don't care, but I just want to recover the whole picture to explain what I see. Okay. So let me just give a couple of examples to illustrate what we can do in different settings. So this is a kind of example I used many times as a collected by my collaborator, Marlin Novak. So in archaeology, they really want to understand why we are different, right? We are from different areas and look different. Why is that case? So they measure the 8 features, including gender, cranial size, and so on. So you can see just from this data set, you can just apply traditional method, PC, together with the kernel-based condition you can test. You can discover this causal graph. It's very informative because with the causal graph, where each link represents a direct causal influence, you can easily distinguish from between cause and effect, and you can even distinguish between direct and indirect causal influences given the set of variables. So it's very nice. And here we assume there are no latent variable, no latent compounder, and then you can go further. Now, if you are willing to assume something about the causal mechanism, then all of a sudden the causal structure is fully identifiable. For instance, if you assume it's linear non-Gaussian, then the causal structure is fully identifiable. And you can even extend the result to some scenarios with latent variables. The same thing happened to post-nonlinear model and additive knot model. Of course, they have to pay the price, right? In some cases, you may not really know what kind of properties the causal mechanism may follow. Then wrong assumptions about the causal mechanism can give you very bad results. But at least this means that, yes, with some side information, you can even distinguish between cause and effect, given 2 variables without the technical information. And here, let's have a look at another real data set. Here, you can see in psychometrics, they try to see the underlying mental conditions, right? You cannot directly touch or measure the underlying personality traits. Instead, you can only measure something, right? Usually design some questionnaires and collect answer scores, and they try to make use of their understanding to derive or to define those dimensions, including openness, conscientiousness, and so on. But the best way or a better way is to automatically discover what's going on, right? To explain the data. So right here, they design a lot of 50 questions covering those dimensions they believe can explain the situation, including extroversion, neuroticism, agreeableness, and so on. So now we just use the answer scores. Now you can see with some methods, you can really discover a very clear picture on the to explain the data. The first method I will introduce is called the rank deficient constraint-based method. The idea is very clear, very simple. So in the linear Gaussian case or just linear case, you can just try to see whether a set of variables can be separated from another set of variables by making use of some bottleneck. And if the bottleneck has lower dimensionality, then this observation has some graphical implication. Okay, by making use of this very simple observation, you can discover everything right here, including the latent variables and the relation among the latent variables. In the linear Gaussian case, you can just recover the equivalence class right here. But basically, you know where the latent variables should be and how they are connected. And you can even make it better by recently, we extended the work by allowing each of those variables to be latent or observed. Essentially, it's very flexible. Now you can see the application. This is the result on the data set I just showed. So right here, we have 50 questions denoted by O, I, O questions, A, E questions, N questions, A questions, and C questions right here. And error variables are the latent variables automatically learned from data. So now you can see, yes, even for O questions, we have actually 3 dimensions instead of a single dimension. They are right here. L4 explains imagination. L6 explains understanding. And L5 corresponds to something like a creativity. So basically, when we say it's openness, basically, right, as you can see from here, it has 3 dimensions: understanding, imagination, and creativity. And furthermore, you can see creativity is the effect of understanding and imagination. It's very nice. We can all just discover those dimensions from data. And they seem to be very plausible, right? And similarly, you can see what's underlying the agreeable, the A questions, E questions, and so on. And you can also see the causal relations among the discovered latent variables. This is meaningful because if I try to change one dimension of my personality, I try to make use of this causal picture to see what to change, right, to achieve my goal. Okay. And the second method I would like to mention is in generalized independent condition method. basically the idea is also very, very simple. You just want to see whether combinations of the measured variables, X variables, are independent in the linear non-Gaussian case. If they are independent, then you can see some information about the latent variables. That's it. As a special case, we have an independent noise condition, right? If you regress the effect on the causes, then the regression residual will be independent from the hypothetical causes. That's independent noise condition. Now, this is basically almost the same thing. You just consider two combinations of the measured variables. You see whether they are independent, and then you immediately see something about the graph. Okay. And here you can see a result. By making use of this condition, you can first find the causal cluster to see where the latent variables are, and then you can discover the relations or causal orders of the latent variables done by a firm right there. And here you can see application on the teacher's burnout data. So right here, we have 28 measured variables, and we automatically discover a number of latent variables. On the right, this is the hypothesized model by experts. And the discovered information from data basically is consistent with the model given by experts, right? That means two things. First of all, yes, data is good. We can make use of data to really look into the process behind the data. And the second of all, the expert model, hypothesis model by experts is also very good because it perfectly explains the data. Okay, now let's have a very quick look at non-ID situations, because in a non-ID situation, usually discovering the underlying causal process would be simpler. Why? Because causality is about the changes. If everything ID, then may not really make sense to talk about the causality. First, let's have a look at the temporal information. Here, this is the setting. Suppose this is video data, and video data can be seen as a high-dimensional invertible function of some underlying latent processes or concepts, right? And you try to recover those underlying concepts, objects, and so on from the pixel values in the video data. Okay, now it's very interesting that in a very general situation, you can still recover all the latent processes almost uniquely. And even if this function, mixing function, mapping function from the latent processes to what we see, right, in the observed data, is non-parametric, and the causal relations among the latent processes, time-delayed correlation among the latent processes, is also non-parametric. You can still recover the latent process up to the component-wise transformation, meaning that each latent process can be recovered up to itself. Okay, I'll give some examples. Let's look at a second example. Oh, there's no animation because it's PDF instead of the keynote document. So right here, if I play the video, you can see 5 balls in different colors move around right here. You have this video data as the input, and then the procedure will tell you that, oh, here, 10 variables, latent processes are very interesting. Turns out that those 10 learned latent processes are nothing but X and Y coordinates of the 5 balls. So basically, you learn that, oh, those balls are interesting. At the same time, you can learn the time-delayed causal relations among the balls. Why? Because between some pairs of balls, there's a hidden spring. So they are the causal influence in between. You can recover the meaningful variables and the relations at the same time if you have temporal data, as you can see from here. And you can go further. For instance, in reinforcement learning, you want to understand meaningful states, right? Usually, right now with deep reinforcement learning, we just have raw input, like video data as input. You may want to understand what's going on, and you may want to provide a visualization or interpretation of the underlying states that you have to rely on for decision making. So in this work, we just divide the underlying state representation into 4 categories, as you can see from here, according to whether they are controllable and reward relevant. For instance, here, if you drive, right, speed position would be controllable and also reward relevant. And music, for instance, right here, would be controllable, but it's not reward relevant if you just care about driving. And right here, the interesting thing is that from the raw data, say pixel level video data, you can recover those 3 categories right here from the data with identifiability guarantees. And this way you can see what I can control and what I cannot control, but I have to pay attention to. Right here, I cannot control it, but my decision has to rely on this kind of category of the representation. For instance, you have to pay attention to the road condition, right? You cannot control it, but your decision has to rely on the road condition. We can discover all those categories, and then this way can make reinforcement learning really interpretable. At the same time, you can quickly adapt to a new environment because you have a better understanding of the underlying process. Okay, I have a couple of minutes. Now let's go further. Previously, I talked about the temporal data. Now, suppose we have distribution shift. We have multiple distributions. What can we do? So basically, we know that non-stationarity or heterogeneity is really popular. If you have a long time series, as time goes on, the value of some background variable could be different, right? As a consequence, the data will be non-stationary. If you collect data under different conditions, then distribution can be different. So let's see how we can, why we have non-stationarity and how we can deal with such a thing. In statistics, non-stationarity is horrible because if you have non-stationary data, then you cannot just use the same model, right, to analyze the data. And the estimation efficiency could be worse. But from a causal perspective, essentially causal modeling and distribution shift are heavily coupled. If I know causal model, because of modularity, I know they can change, and those changes will be independent, right? And that means that if I observe a distribution shift, I can try to infer what kind of causal model can lead to this kind of change, and then I can quickly discover the underlying causal process. So here, by changing causal relation, I mean relations can be stronger or weaker and disappear, and so on. So this is the kind of work we did a long time ago. So in this work, you can make use of non-stationarity, and you have additional information to discover causal direction, and you can avoid fake or spurious relations. And I will skip the application right here. Now, previously, we just assumed that the causal relation among the measured variables are interesting, but you may want to go further. In many cases, we have non-stationary data, but the non-stationary data, we have non-stationarity because the distribution of some of the underlying components may change. As you can see from here, we have a generating process to generate X, which is observed, and we have a lot of underlying components. And now we try to explain why the distribution of X has been different, right? So in this work, we assume that there's a minimal set of variables, underlying hidden variables, whose distribution can change to explain the change in the joint distribution of the data. And at the same time, clearly there is a lot of other variables, hidden variables, right? Or even noise. And their distribution is the same across different scenarios. It's just stationary kind of noise thing. And then you can show that this changing part, the changing component can be recovered uniquely, meaning that you can really understand why the situation, the distribution has been changing. And as an immediate application, you can use this for domain adaptation. Why? Because you have multiple distributions. Now you can try to find a minimal way to explain why the distribution is changing. If you can find this model, you can automatically figure out what has been changed, right, in the new scenario and how to align the distribution, because you know how the thing can change. If you understand that, you can try to find a way to align the joint distribution across different datasets or domains, and then if they are aligned clearly, you can easily make use of source domain data to make prediction. As you can see from here, so we have this is the method, the result given by this method. The prediction performance is pretty good. I think meaning was here, right? Oh, you're not big. I forgot it. And now let's consider another problem. Try to go further. In deep learning, right now, generative AI is so popular, right? So you can use Stable Diffusion, ChatGPT to generate a lot of text or images. So if you really play with ChatGPT or the Stable Diffusion, you can see in many cases, right, you have very good answers. But in some situations where you believe that the question or the prompt is new, then the generated result could be kind of ridiculous, right? Why could that happen? Basically, we can see that they don't really have the concepts, the idea of the concept that we have. I don't have an example here. In my class, I usually use a number of examples to illustrate that. We make use of concepts while they make use of data distribution. And very often they still do some kind of smart interpolation instead of extrapolation. Why? Because if you want to go beyond the data, you have to really understand what things are, what kind of operation you can apply, right, to the things to give an answer. Now, let's consider one specific problem, image-to-image translation or data generation. They are very similar. We have two data sets right here, two sets of images. One of them is taken in the summer. The other is taken in the winter. So we have two sets of images. They are not paired. We don't have pairing information. Now, the problem is that follows. Suppose you are given an arbitrary picture taken in the summer. Can you just automatically produce a counterpart of this picture taken in the winter? Right. For instance, you have my picture, and then you want to translate my photo to anime, right? So this is a kind of legitimate question. It's very important in machine learning, and it's also related to generative AI because it's about how you can really understand a particular concept and change it, right, in a good way. So at the first glance, you may say this problem is zero-posed because I don't have pairing information. Mathematically speaking, it's like going from the marginal distribution to the joint distribution. We know it's not possible without the further information, right? So we have to make further assumptions. One particular assumption we made is a minimal change assumption. Basically, in this context, you can see if you try to produce an image, you have content and style. And in this case, you will say the content would be the same. I still want to basically have the picture of the same mountain, the same scene, but the season has been different, right? So season, effect of season would be style. The problem is how we can really make use of some principle so that we can go from the marginal distribution to the joint distribution of the data, right? So here, we show that if you assume that the change in the style is minimal, in the sense that the number of components corresponding to style is as minimal as possible, then actually the whole process is identified. By that, I mean, you can really understand what you mean by season, and you can really see the effect of season on the picture. You can see how, right, each pixel should be changed according to different seasons. And here you can see one result. The idea is very clear. And here we have two unpaired data sets corresponding to a female and male. Okay? And then you want to do either generation or translation. So this is the generation task. Now, please generate two pictures corresponding to different genders, but with the same content. Now you can see the result given by different methods. This is the style gain. This is the tensor gain. And here, this is our result. You can see they are basically the same person, but clearly the gender is different, right? You really avoid any unnecessary change. You try to preserve the information. In other words, you can really allow the machine to understand what you mean by gender and how to really reflect the information of gender in the final observations. Okay, so this has a lot of implications in generative AI because you have to understand, you have to allow the machine to understand what the concepts, right? You have to find the right operations that the machine can follow. Now let me spend 1 minute on, I'm running late. Okay, so to discuss some possible challenges in this space. First of all, right now, when we talk about causal representation learning, we just try to recover the latent variables, right? Latent confounders and the relation among the components and so on. But in many cases, actually, we don't really have latent common causes. Instead, we have selection. Inside our body, a lot of the genes are dependent. They are dependent not because one of them is the cause of the other. Instead, in some way, they have to kind of work together in a specific way in order for us to survive. We have selection. And in many cases, even if you talk about language, the language or text, right, dependent tokens are dependent, not just because of the causal influence from the confounders. Instead, we have selection, right? If I can use this sequence of tokens to make myself clear, I will use it. Otherwise, I will not use it. So I think it's really important to make selection process very clear and then make the causal representation learning based on selection process very clear. And in the ID case, usually we have to assume some parameter forms. What if the system is really kind of complex, right? What can we do? So there are some technical challenges right here, but I believe it can be solved within years. And And if you want to deal with a real problem like video understanding, so you have to go from the formulation of the causal principles, right? Also to a lot of practical issues. So right now, Mimi and I are working on this problem. Okay, so to summarize, a lot of tasks rely on some kind of representation. And causal representation seems to be a fundamental type of representation. For instance, if you want to make decisions, clearly you have to foresee, you have to see what you can change, and you have to foresee the consequences of different possible actions. And if you want to achieve unfairness, right, in machine learning, you have to really make use of the causal process, the process view, because eventually you want to change the world. You want to apply something so that finally you can achieve fairness in the data. And how can we really achieve causal representation or causal structure from data? First of all, we have to formulate the causal principles, for which I mentioned some, and you have to make the principle technically operational. And very important issue is about identifiability. So generally speaking, in a non-ID situation, you can easily develop some very strong identifiability results, even if the system is non-parametric. And in the ID case, you usually have to benefit from some parameter constraints. Thank you very much. That's it.
One quick question: when you try to discover the latent variables, what kind of assumption do you impose on the latent variables, and how actually do you map to the latent variable to the concepts in practice?
Oh, great. Basically, there are two questions, right? The first one is under what condition you can really discover the latent compounders with a guarantee, right? So you can see a number of works here. Let me give one example. Okay, this one is slightly more complex. Let me go to this one. So here, from working on this problem. So basically here, you can see the following thing. I try to see whether there are latent variables right here. And then you can observe the following thing. The linear combination of, say, 1, 2, 3 will be independent from 4 and 6. Why? Because in the linear combination, you can try to remove the influence of the two latent variables. And this linear combination will contain only the noise terms in the measured variables. As a consequence, this linear combination, as a combination of noise terms, will be independent from all the remaining variables. Now, given that under some graphical conditions, you can be sure that, yes, there must be two latent compounders right here. And then if you assume something about the underlying structure, most of the time, you assume something about the sparsity. Then you can just show that this is the only solution, this is the only answer, given the set of the independent relations you can discover from data. So this is the first one. Of course, this is the linear non-Gaussian case. In the linear Gaussian case, it's the same thing. And in the temporal case, it's also the same thing. So you just, under your assumptions on the structure, you can show that, yes, if I discover this pattern, then this is the only way to explain that pattern, right? The only way of the structure of the process to generate that dependence relationship or independence constraints. And regarding the second one, is about how you can make sure that discovered latent variables correspond to concepts, right? So I would say that's very hard. And that may involve, first of all, when we say concept, that is our definition, right? It's meaningful to us. Let's say it's a concept. And for machines, if you think of yourself as a machine, you automatically discover those concepts by making use of not only this kind of data, but also some supervision or side information, right? You are, some people told you, oh, pay attention to this. And sometimes you can also move around and do interventions. Then you can be sure that, oh, right here, I have to pay attention to this particular thing, this concept. By that, I mean the following thing. Right now, we are trying to take a very challenging problem. We don't make use of any side information. If you want to really align the learned latent variables with the concepts we make use of, then it's very essential to make use of some kind of weak side information. Yeah, like you can make use of semi-super learning, right? Or you can make use of some constraints. You can try to find a way to formulate what you mean by the concept, and then machine can automatically enforce such a condition to align machine understanding and what we have in mind. Did that answer your question? Thank you.
Okay, great presentation. And thanks for Professor Kun Zhang. And I want to invite our chair of this conference to make a comment of our conference.
Okay, I think we have a very good talk this afternoon, and unfortunately, due to the time constraint, I think we have a lot of questions actually, even for me. But I think it's better to ask also afterwards. So actually, so just shows this afternoon the interaction between the machine learning and the causal is a very big area. So there are more than just the authors talk about today. I think there are others, but I think actually Dr. Zhang has a good review about some of those problems. And but we are not done yet, so we have evening session online only. I think starts 7 o'clock. Is that right? Okay, 7:25 we'll have online section. So we still some interesting talk still going on. So for the people, I encourage you to go to online section. Okay, thank you very much for today. Bye bye for the speaker too.